I was getting my other pad because this pad is hard to rip out. And it was hard.
Let's go with that. All right. Let me hand these guys around. I'll bring it up on the screen. Can't see anything. No. Up here, right here. We're going to be looking at this guy. I'll have it under the doc cam in a second, but this file here, for people online. I just wanted to get that for people to see. This is intended to look fair amount like a handout with different charge distributions, which is like you got, right? Yeah, okay. Yeah. The charge distributions from maybe chapter 26 or so. We had a similar looking. Oh, I didn't bring my face shield. Didn't grab it. I think I'm going to do this. So this guy is, let's see. This guy is right here called, nope, key current distributions. And in comparison, there was key charge distributions. This guy from back in chapter 26, and we kind of filled in some equations here with the electric field for a long line charge, a plane of charge, point charge, which was the main one. And so today, today we're going to be kind of working on filling in some of these. These are all in the chapter summary for chapter 32, and they are all kind of specific worked out instances of the general fact. And the general fact is written, where is it? Written at the end of class Monday. So I think I'll transition over here. For people online, I'll stop sharing and just show the document cam. And go to the other camera and put you guys on the doc cam. So this was something we had stated at the end of Monday's class, the Biot-Savart law. How do you find, maybe in this version here, because if you look at all the examples on the handout, there's a current flowing in some shaped wire. How much current? That's probably I. The main difference between the three arrangements is what is the shape of the current? Basically, what is the shape of the wire? What kind of path do we have? And we'll see how that affects the results. So the general fact is said right here, kind of trying to sketch it out here a little bit. Let me extend this line down to separate the electric stuff on the right. So this was electric over here. If you're a certain distance away, the electric field points away from a positive charge, and that would be in the positive r hat direction. So as a unit vector, we put the r hat, which means in the direction of increasing radius. Whereas in this case, if we pick this point, we do a cross product of the current direction with the radial direction, the r hat direction, and we get cross product there. And what it basically tells us is something which I was trying to sketch out here, where above the line along which the current is, this little short segment of wire is oriented in this direction. Anywhere on one side of this line, you basically have magnetic field wrapping around this axis. And anywhere, let's say above it, that would wrap and point at us according to right-hand rule. And anywhere below it, it would point in. Now you could do the cross product to get right-hand rule. You could do, you know, first finger is DL, which is pointing this way. Second finger is R hat. I'm going to use this as my, I'll use, maybe this is my example point. So then I kind of rotate my hand from the current direction towards the direction towards pointing at the point of interest, and my thumb points up. So right here we get up, and if I did it anywhere below here, I'd get into the page. The easier way to do that is similarly in keeping with right-hand rule is if you just point your thumb of your right hand in the direction of the current, if you just put the thumb of your right hand in the direction of the DL vector, which is basically the current direction, then your right hand fingers naturally wrap around this red axis in one orientation, and that would be the direction the magnetic field is rolling around it. And if this was the only short segment of current, which is kind of a weird thought, like if the current came from nowhere and just existed for like a millimeter, you would have a really strong magnetic field if you're close to it and if you're kind of perpendicular to it. So you have really, the strongest magnetic field would be kind of in a wall like this, and would get weaker as you head forward towards the line straight ahead where it dropped to zero, and it would get weaker as you kind of move back from this wall towards the line directly behind. Because if you're directly ahead, your cross product is zero, and if you're directly behind, you're crossing two vectors that are kind of opposite to one another, and you get zero for anti-parallel vectors. So this is often called the Biot-Savart law, and it's often written in differential form. So if you tell me a small segment of current DL, it calculates for you, or it expresses for you the small amount of magnetic field due to that. And it's usually written that way because instead of just doing B and L, we usually can't do B and L because your distance from different segments of the wire would be different. So we do it differentially in a differential form, and then we want to integrate this. If you give me the shape of the current, I'll integrate this expression over all segments of the wire, and I will see how much each segment of the wire contributes magnetic field to a certain point, and I will sum it up. And we're just going to do that once or twice today to fill in some of the entries on here, but the answers again are in the chapter summary for 32. This one is one we're gonna kind of work through. And then this one is actually one of the easier ones. On the axis, we're only gonna have a formula in this case, which you saw in last week's lab for magnetic field on the axis. You can come up with something similar for other spots. And then just to compare here, this is a current loop. This is a bar magnet. They're basically the same. And if we made some identifications of some geometric factors here with some factors over here, we can kind of write kind of one common version for both. So the three that we're kind of most interested in is, I think this one makes some sense, long straight wire. And that should look, I think, analogous to, where is it right behind here? Electric field's right behind here. You know, one of our interesting charge ranges is what if you just have a long wire with a charge density on it? So what if you have the wire with the charge sitting there? You get an electric field that spikes like this. What if you could almost think of this picture as you pick up this charged wire and then you move it to the right. So now you have charge in motion, you have current in addition to charge, current to the right. And in that case, the magnetic field wraps around in this way we were just saying, thumb in the direction of the current. Easiest way to do it is like grab the wire with your right hand, thumb pointing in the direction of the current, and your fingers circulate in the direction of the magnetic field. So I grab the wire, this is the end on view, current's coming at me, a dot. I grab the wire with the thumb pointing at me and my fingers circulate counterclockwise. And I think we mentioned this before, with right hand rule, essentially the associations of right hand rule are at the viewer is kind of the positive direction and counterclockwise is kind of the positive direction. So at the viewer and counterclockwise tend to kind of show up together, and away from the viewer and clockwise maybe show up together as well. So how strong is magnetic field a certain distance r away? We'll get that one, and then we'll do this one on the axis, and then the third, so along the axis of a circular current loop. And if we were to kind of change the geometry a little bit, we could make some slightly different geometric identifications, and we could be a different shape loop, could be a square loop or something like that. What turns out to be most relevant here is the area, the current, the number of wrappings if there's more than one, and the area enclosed by the loop. If it's circular, that's pi r squared. If it's not circular, you could do something else, and kind of wherever you see pi r squared for this formula, you could replace it with area of the new loop. And then what is this one supposed to be? What is the current arrangement supposed to be here? Oh, I didn't quite label this fully. This was, I need to have I pointing down. I need to have I pointing around these wrappings in some way. It was supposed to be the same orientation as this, so I get the same direction magnetic field. So this is like currents coming down the front side into the page at the bottom, up the backside, out of the page at the top, kind of down the front. So this is all the current. So what is this supposed to look like? It's a big tube of a bunch of wrappings. And what we're going to find to be true here is indicated already by the sketch. I probably should have done one more red line right about there. The spacing of the red lines is supposed to be semi-steady. I didn't spend too much time spacing it out, but it's a uniform magnetic field. It's the same strength magnetic field here as here as here. If you're near the top of the inside of the tube, same strength magnetic field as if you're right in the middle axis of the tube. So this is a uniform magnetic field of just a constant value inside the tube and very small to zero magnetic field outside the tube. Of course, if you did this end on, maybe I should have done an end on view of this one, somewhat similar to like the end on, and like this. What would the end on view look like here? You'd see the current rolling around in a circle, and everywhere inside there'd be equally spaced dots of magnetic field spiking at you, and there'd be zero magnetic field outside. So, so I put P right there, but really P could be anywhere. I could almost just say, what's P right there? What's the magnetic field at P? Oh, that's the wrong color. What's the magnetic field at P? What's the magnetic field at this P? Because it's the same value everywhere inside that volume of this guy. And this is called a solenoid, typically. Okay, let's kind of imagine setting up the integral for this one. Good practice with kind of using a formula that involves maybe a differential and then setting up some integral with some limits to try to cover the entire length of this, because we have a handy dandy ready to go formula right here, which says this is the magnetic field due to each little short segment of this wire. And by the way, this one here called the Biot-Savart law, this should be taken to be somewhat like Coulomb's law. Conceptually, I would think of this as, what is the basis of this equation? Experimental observations. So this is like kind of the grounding in experiment. Like if you do your experiments, this is what seems to be true about the magnetic field. And then from here, we're going to derive specific equations for these other specific shapes. But I'm not going to really justify this. We're just going to say like experiment justifies this essentially. And maybe it looks familiar to us. It has very strong echoes of other formulas we've seen, but the ultimate justification is this is the results when you get out your measuring devices. Okay, so let's do a long straight wire on here. And I'm going to kind of label some things. I'm going to pick a certain segment of the wire and be my DL. And let's see, can we get all that on there? So here's my wire again. But right now, it's all carrying current I. But right now, I'm just going to kind of imagine a small arbitrary chunk of the wire right here. Maybe I'll have an x-axis, and this will be like x equals 0, and this is the x-axis. And so the segment I'm interested in has length dx, kind of like dl, I think I'll call it dx, and it's sitting at position x. And it's carrying current, it's all carrying the same current in that direction. So here's my IDL, I'm going to call it dx this time. And then I need a point of interest, a point to observe this at. And I'm going to say my point of interest is maybe just right above the origin at a distance r. So here's my point P. I would like to know what is the magnetic field at P due to this small chunk of wire. And then I'll step back, and what will I do? I'll put integration parameters. I'll put a lower and upper limit on x to cover however much of the wire I want to cover. And I'm going to want to cover basically x is negative infinity to positive infinity to describe a very long wire, but you could change the limits at that stage. It's easy to change the limits. Okay, so now let's try applying this fact here. I need to express everything in here, mu naught and 4 pi, that's not going to be an issue. I need to express everything in here in terms of the constants, which would be like mu naught, 4 pi, I will be a constant. And then R, how far away from the wire is point P. I can express, and now we get in a little bit of trouble with R, because we might want R to mean a couple things. We might want R to mean the perpendicular distance from P to the wire. but we might want R to mean the distance from this chunk to the wire. They're both kind of relevant. I think I'm going to call this distance, I think this is what I did before. I think I'm going to call this distance D. And then in the work that you see above, this would be R. This is the radius vector. Radius vector points from the source to the point of interest. So that's going to be the radius vector, and X is the variable. So I want to express everything up here in terms of, here are the good, we got some constants. The constants, of course, would be like mu naught, I, and D. I'm not going to move my distance from the wire. And then the variable, which would be like X, and along with X, I'll say, you know, dx. So I want to express everything in terms of those guys. In particular, I want to express things like the cross product in terms of X's and dx's, and the radius in terms of X's and dx's. So the first one up is pretty easy. The denominator is radius squared. So what's the radius? And now radius here, I do mean distance from the short segment. This is the source. So what is R? Well, clearly from Pythagorean theorem, you know, one of the substitutions we're going to need is R squared is D squared plus X squared. So I got that guy. What's DL? DL is DX. That's basically just the same name. Okay. And now we would like to do this cross product. You can't leave R hat inside of an integral because R hat could point in different directions from every segment. You would want to express that. So I would like to kind of work this out in terms of unit vectors. So, you know, my DL vector is dx I hat. I should give myself a little more space. And then what's my radius vector? Well, essentially you could do this a couple different ways. You could do it this way. My radius vector is, what is this vector? Well, it's got an X component of negative X I hat and a Y component of positive D J hat. Does that look about right? This actually already says the top one. This implies the top one because if you take the magnitude of this, you just do X component squared plus Y component squared. So being a little redundant. So this is my R vector. This is not R hat, this is R. And up above, there's an R hat, right? So how do you deal with that? Well, R hat is just the length of a vector divided by the vector divided by the length. So it is negative X over R I hat plus D over R J hat. Does that make sense to you? What's the unit vector in a certain direction? It's just the vector that points in that direction divided by the magnitude of the vector. So we're going to have another factor of R in the denominator, right? We have R squared in the denominator already, but we really have another R in the denominator when we kind of do our, you can think of these as sines and cosines. Does this look a little bit like a cosine and a sine? What's the cosine of this angle right here? X over R. This is basically saying negative cosine theta times magnitude. And this would be, what's the sine of this angle? So you could think of these very much as sine and cosine of this angle. And if you wanted to, you could do the cross product by thinking of it as magnitude of the first vector, which is dx, magnitude of the second vector. Well, what's the magnitude of the R hat vector? 1 times sine of the angle between them. So I think what's going to really matter here, probably when we do the cross product, is which of these two terms is going to matter more. The perpendicular component, which is the component that's perpendicular to the current direction. So all that's really going to matter is this dr one here. Do you get magnetic field in the positive k hat or the negative k hat at point P due to current flowing that way? Well, you could do the cross product I hat cross I hat is 0, I hat cross j hat is positive k hat, or you could do your right hand rule and it points out anywhere above here and it points in anywhere below here. So I think we're going to get that dB. There's a little bit of magnetic field right there. In which direction does the little bit of magnetic field point? I think I'm going to try to draw it in 3D. Here's the little bit of magnetic field pointing kind of at us. That's supposed to be out But we could just write out, does that work out? Oh, I should have mu naught over 4 pi I dx I hat cross, I lost it, negative x over r I hat plus d over r j hat, and then it's all over r squared. And at some point I'll substitute in the r squared is d squared plus x squared. So what happens to the cross product? It should work out. I cross j is k, and we just get d over r. So I end up getting mu naught over 4 pi I d j hat, and I'm going to kind of cluster things a little bit. I'm putting all the constants out there. D is a constant, I is a constant, mu naught over 4 pi are constants, j hat, or sorry, it's k hat. K hat is a constant unit vector, so it's a constant. And then what's left, I have a 1 over r and a 1 over r squared, and I think I have 1 over r cubed. Did I miss anything? I don't think so. I missed one thing. I need a dx, something to integrate with respect to dx. So that's my dB. So if you think about it, directionally, what is it saying about every little segment of current is creating magnetic field pointing straight out of the page. They're not competing. They're not kind of working kind of together and kind of against each other. Every little section of the wire is creating a magnetic field that points straight at us, except the nearby sections of the wire are creating a stronger magnetic field because they're at a smaller radius. And they're also at a better perpendicular angle, which is maybe where the extra r cubed comes, with the extra factor of r taking it from squared to cubed. So we just need to do this. So we need to now like look up an integral basically for something like this. Let me get that at the top. We need to basically look up an integral for what is the full magnetic field. The full magnetic field is the integral of the small magnetic field contributions, and that would be mu naught I d 4 pi, it's all in the k hat direction, integral, d squared plus x squared to the 3 halves dx. That look about right. R cubed is this quantity to the 3 halves, and then we should put limits on it. And up until now, we haven't at any point up until maybe the next step said anything about how long the wire is. At this point, we could have it be a finite wire. We could have it be infinite in one direction and start at any particular x coordinate we want, or we could put negative infinity to infinity. And if for an infinitely long wire, I'm going to choose limits of, you know, x1 is negative infinity to x2 is positive infinity. So basically x1 should be the left end of the wire and x2 should be the right end of the wire. And that's relative to choosing p to be at x equals 0. Well, if it's infinite, all this stuff doesn't matter. But if it were finite, that would matter. So I think I'll just say, you know, let's integrate from negative infinity to positive infinity. And then we could just kind of look up this antiderivative, or we could do this integral however we want. And it's not all that different. There are differences, but if you were to think back or look at work in chapter 26 to integrate the charge distribution of an infinitely long wire, you would see a lot of this similar stuff show up. The directions would be very different for the electric stuff. The electric stuff would spike away from the wire, like in the positive j hat. The magnetic stuff wraps around the wire, which above the wire is the positive k hat. But you'd end up with constants. You'd probably have not, what would you have instead of mu naught in the numerator? You'd have epsilon naught in the denominator. Instead of I describing how much current there is in the wire, you'd have lambda describing how densely charged the wire is. And lots of other stuff would be very similar. What might be different is you might have a factor of x in here in the numerator instead of a constant d out there. In fact, I think one component maybe came in with like the constant d and the other one came with an x, which would change the integral, you know, to have another factor of x somewhere floating around. So that's not the easiest antiderivative, but it's actually basically the same antiderivative as the one that mattered most for the infinitely long wire as well. Infinitely long line of charge. And just kind of go back to where I think this one is mentioned in the appendices. Appendix A about math facts, and kind of take it right from here. I think it's this top one. We probably use almost this exact same one before. X squared plus D squared. So where they have A, we'll write D. We want the positive because it's X squared plus D squared representing radius, kind of 3/2 power, good. The numerator doesn't have a factor. Here it has a factor of X if you needed it, but we don't. So you get positive X, which again, we're going to take the limit to plus minus infinity, but positive X over D squared square root of X squared plus D squared. I'm just going to kind of, that's the antiderivative. And so the antiderivative would be mu naught I D 4 pi. The direction isn't ever going to change. It's going to be k hat. And I need to zoom out. And then I'll just say my limits are negative infinity, positive infinity, and we got a D squared and a D squared plus X squared square root and an X. What does D mean? At this point, I could kind of go back from calling it D to calling it R, because I don't have so much the confusion now between which radius do I mean. Do I mean radius from a point, or do I mean radius from a wire? The D is the perpendicular distance from the wire. Okay, what happens when you do that, when you do the limits? Well, I could take the D squared out, right? The D squared is a constant, and this D or D squared becomes inverse D, which is basically one of the main results of the calculation. If you double your distance from the wire, what happens to the magnetic field? It's inversely proportional to D. And then there's a D squared here, but what's the limits here? If you take the D squared out, in fact, I think I'll do that. I'll just kind of put that D squared right there. And then what happens to this in the limit? If X is super far to the right, like you're 10 centimeters above the wire, but the right edge of the wire is 100 miles away, what's this fraction? 1. And when you plug in negative infinity to be -1, you get 1 minus -1 is 2. So this would be 1 minus -1 is 2. You know, the D squared becomes irrelevant in the limit, and you get X over square root of X squared, so you get X over the magnitude of X. So we get a factor of 2. So instead of 4 pi in the denominator, we would usually write this mu naught I over 2 pi k hat b, and then I could do D, or you could often call it radius R. And that would be our result. And if you're to compare that, by the way, to the answer for the electric field, what's the formula for the electric field? Maybe I'll keep that closer. What's the formula for the electric field that we put down on this sheet, you know, a month ago or so? It would have been right here. The formula for the electric field was electric field. I might have written in terms of K. Now I'm going to write in terms of epsilon naught. I think I'm just going to write it like this. It'd be 2 pi epsilon naught lambda 1 over R. And this is equivalent to 2K lambda if you want to use K. But let's go this way because it'll make the connections, I think, stand out a little more. Over 2 pi epsilon naught, how strongly charged the wire? 1 over radius. And our answer right here is 1 over 2 pi, mu naught over 2 pi. How strong is the wire? Current I, and divide by radius, basically. The directions are very different. Directions here would be something like, kind of like the R hat direction. Basically, this would be kind of like the R hat direction, which would mean away. Perpendicular R hat. But very similar results. inversely proportional to distance. Not too common. And again, that's an infinitely long wire, but if you wanted to make it finite, all you got to do is rewind not very far, just change those limits right there. And when you're doing that, you'd want to say relative to the position of interest P, where's the left end of the wire X1 and where's the right end of the wire X2. Maybe it comes from infinity and it turns off at 0. You could do half infinite wire, probably get half the result. So that's one of them. That's kind of one of the main ones. And I should write that on my sheet. Write that on my sheet. That one will go right there. And K hat, take that with a grain of salt. That was committing to X and Y, but basically that would be kind of the wrapping direction. I think a more general statement for that would be something like L hat cross R hat. L hat cross R hat for if you wanted to. L hat, the current direction, cross R hat, the direction to the point of interest. But that's getting, I think, more detailed than you needed. If you got this idea of the picture in your mind, the magnitude is mu naught I over 2 pi R. Mu naught I over 2 pi. And what I called D before, I'm now calling R. So I think I'm going to do that. That's more common. All right. This one, I think I'll just kind of say the answer, and then I'm going to look at some graphs of this one, which is related to like last week's lab. What's the answer for this one on the axis? If you remember from last week's lab, we do have our mu naught, we do have our I. I'll put in a factor of n if there's more than one wrapping, multiply by n. Ni, I would kind of think of that as a little cluster, Ni, current times number of wrappings. In this case, there's not, this wasn't 4 pi, it was 1 over 2 pi. This one ends up being 1 over 2. And then what's a little more interesting is, what about the 1 over R here? So mu naught, not 2 pi, this one's a 2. Current. This one is 1 over R with units of 1 over distance. This one, if you remember, was R squared over R squared plus Z squared to the 3/2 power. That says 3/2 power. And what's Z? Z is the distance along the axis. Z equals 0 means the center of the loop. What are the units of this quantity right here? What are the units of R squared over R squared plus Z squared 3/2? It's distance squared over distance cubed. It's 1 over distance. And in this case, there's two relevant distances. There's distance along the axis Z, and there's radius of the circular wire R. So it might be some complicated expression with units of 1 over distance. In this case, how many parameters or how many variables are there in the problem with units of distance? If it's infinitely long, there is no distance needed to describe the wire. The only variable with units of distance is how far away from the wire are you? And sure enough, it's just 1 over that distance. Dimensionally, this works out. What are the units of mu naught? It could be written other ways. Most commonly, the units of mu naught are written in a way that kind of fits this formula very well, or these formulas very well. The units of mu naught are units that when you multiply it by amps and you divide it by meters, you get Tesla. So the units of mu naught are, among other things, Tesla meter over amp. And we're going to unpack that and think about what Tesla means. Tesla, of course, is the unit for magnetic field, but just like volts is related to joules, is related to newtons, et cetera, et cetera, et cetera. Tesla is a composite unit that sometimes it's really nice just label things with Tesla. Just label this variable here with units, this constant here with units of Tesla meter over amp. But sometimes that kind of hides some of the connections from us by kind of burying some of the connections that the units would show us into a new composite unit. So at some point today, we're going to kind of say, what's the connection between Tesla and newtons? That's highly likely to be a test question, like a little front page of a test question, like which of these formulas correctly shows the relationship between Tesla and newtons, or maybe Tesla and joules, or some more familiar unit that's not new to the magnetic field topic. Okay. Let me just say a couple things about this guy here. what does the denominator, what's the square root of r squared plus z squared mean geometrically in this picture? So radius would be, you know, this is radius. Capital R is not a variable radius. Capital R is the fixed radius of this object. What is the denominator? What's the square root of r squared plus z squared mean? The square root of r squared plus z squared is actually how far away we are on the axis from every spit of the wire. You know what I mean? So how far away are you from the center of the wire? Well, z. But how far away are you to sit right there from actually any bit of current? You're, you know, you are r squared plus z squared to the 1/2 power away. And that's kind of what our denominator is showing is it's that cubed. So basically what's this fraction? It's radius squared. It's green squared over purple cubed, kind of. What would happen if we went to extremes? What happens if you kind of slide in here and you get really close to the center of the wire, or you go to the center of the wire? Z goes to 0. And you can also say what happens to the purple distance? It becomes the green distance. So then what is this fraction if you're at the center of the wire? It's just 1 over capital R. What if you go the other way? And let's not go all the way away, because of course if you go super far away, this will become very close to 0. Right? The denominator will grow bigger and bigger and bigger, and the numerator is constant. What if we went pretty far away? What do you think I mean by pretty far away? What if we're at a z value that's maybe not like infinite, but it's quite a bit larger than the other distance in the problem? So what if you're several radiuses away? You're more than 10 radiuses away. But I don't want to say you're a million radiuses away. So if we get into there, what happens here? Z squared kind of dominates the r squared, and we can just make this 1 over z cubed. And that should sound a little familiar for this picture, because what do we call this guy? A magnetic dipole. And on this sheet, oh, that's not the sheet. Which one on this sheet for electric stuff? Which one on this sheet for electric stuff is most in keeping with this arrangement? Well, this one jumps out. That's a long straight wire, and that looks like a long straight wire, and they have a lot in common. But the one that's most in common with this one is this one, the dipole, right? And if we use this one the least, I'd say most likely. But if you look up what were the formulas for the dipole, they involve things like 1 over radius cubed, 1 over distance from the dipole cubed, which would kind of be like saying if you went to a pretty large z value, distance along the axis, you'd get kind of like 1 over z cubed. And then you could make some really strong connections again between this and the formula for the electric field of a dipole, especially if you recall this, we actually had 2 formulas. Do you remember why we wrote 2 formulas in here, or the chapter summary mentioned 2 key formulas? Yeah, it had twice as much information as our magnetic formula had. It said, here's magnetic electric field at one set of key special points on the axis of the dipole, pointing negative to positive Q. And then here's another set of special points, the mid-plane. And they both were 1 over r cubed in dependence, but they were different in direction and different in strength by a factor of 2 or a half. So what if it hadn't been a circular loop? Obviously, everything here is specific to circular loops, but I'm going to say pretty far away, and I'm going to say B is approximately, I'm just going to say for a small loop. And what do I mean by a small loop? The dimensions of the loop are quite a bit smaller than the distance away. You could say this one of 2 ways. I'm pretty far away, or it's a pretty small loop. Take your pick. I mean it to mean the same thing because it's a comparative statement. My distance away is much larger than a dimension of the loop. If you did that, the denominator just becomes z cubed. And then we're going to do a little bit of something here. And we're going to write this away that might seem a little odd, but I'm going to write 2 pi. And I'm over here going to write ni pi r squared. Is that correct? If I go to this limit, then I can make the denominator just z cubed. and I just threw a pi into top and bottom. Why did I choose to throw a pi into the top and bottom? It was my choice, but why do you think I might have done that? This starts to look like something we've mentioned before about a current loop. We call this the magnetic moment of the current loop previously. Number of wrappings, if there's more than one, times current times area enclosed. So you'd get a slightly different formula if you did a square loop. Maybe you did a square loop that's, like, with the same diameter as this circle. You get a little bit different value if you're close by, but if you're pretty far away, you'd get basically about, maybe I should do it differently. If you replace this circular loop with a square loop of the same area, you would get a slightly different magnetic field if you're nearby or at the center. But as you go further and further away, those details of the geometry of that small little loop over there become less meaningful. And what mainly stands out is this quantity that on Monday we called the magnetic dipole moment. So what if you wanted to do a formula for this guy? You'd kind of say Z is the distance along the axis, and then you would just have some way to like measure or report how strong of a magnet is this. And the number that would be used to describe how strong the magnet is would be mu. Not mu naught, magnetic dipole moment mu, which is NIA. And what are the units of mu? As we said it before, it's got units of amp meters squared. And you could do something like that. Last one, I'm just gonna draw some graphs. We're gonna look at some graphs, but I'm gonna say the answer here right now. In comparison, what do we have to do to get a magnetic field? We have to do mu naught. We probably have to multiply by current. There's probably some constants. And then we have to write something with units of length in the denominator. Yeah? What was the key unit of length here? There was only one option, 1 over r. Here it was more complicated. What about here? What unit of length is going to be relevant to this problem? And I'm going to tell you what it's not. It seems like it might matter what the radius of the loop is, since that was so important in the previous panel. But in this panel, I'm telling you it's the same magnetic field everywhere inside, whether it's a small loop or a medium-sized loop. Actually, the radius cancels out of this geometry if it's an infinitely long or very long solenoid. So we have to still do something with units of length in the denominator dimensionally, and it ends up going a little bit like this. So we're going to have our mu naught, we're going to have our I. I'm going to tell you there is no constant in this one. There is no 1 over 2 or 1 over 2 pi or 2 pi. It's just mu naught I. So the constant's kind of like a 1. And then we have to do something. Oh, maybe I should do an n. And what we're going to do here is n over L. I'm going to write the n over there. What do you think I mean by capital N and capital L? Let's imagine there's an actual physical solenoid. So not an ideal solenoid that's infinitely long, like an actual physical solenoid. It would have a finite number of wrappings. It might be large. And then it would have a length. And what actually matters is not the number of wrappings, but how densely packed the wrappings are. So how do you make the solenoid stronger? Well, you pump more current through it. That'll definitely do it. Just increase the current in the wire. That'll increase the magnetic field everywhere. Other than that, how do you make it kind of stronger? You have like 10 wrappings per centimeter instead of only 5 wrappings per centimeter. So this is often written as lowercase n. Capital N would have units of wrappings, basically no units. Capital L would be L. So you could just say, like, let's just take this tube, which essentially goes on forever, and let's just kind of take a swath of it and chop it off and count how many wrappings are there and what's the length. And the density of wrappings per unit length is what's most relevant to the strength inside the solenoid. So it's mu naught I little n, and n is the density of wrappings per, not per unit volume, not per unit area, meaning density per unit length. And of course, for a finite solenoid, you could just say it's got 400 wrappings and it's 4 centimeters long. But for an infinite solenoid, you would say it has 100 wrappings per centimeter, which would be, what would that be per meter? 100 wrappings per centimeter times 100 So like 10,000 wrappings per meter. I'm gonna maybe just look at some graphs to kind of justify this one a little bit. So I think I'm gonna share the screen and kind of flip over for the people online and flip over. Oh, there's a chat. Oh, issues with the internet across campus, somewhere on campus. So I'm gonna share the screen. I'm gonna go to Desmos here and PC. Oh, didn't get to Desmos that I meant to get to. Well, that's not how you spell that. Gosh, that's better. Okay, log in. We got a lot of these guys. Carlone calculator, anybody? Approximating square roots, power in parallel, Euler line triangle. I am looking for Helmholtz coil. I thought I saved it last week. Okay, circular coil, which maybe I'll just say, this is, plotting the circular coil formula on the axis. This was somebody's data, I think, from last week. Kind of that kind of look to it. That's a single coil. And you can think of a solenoid as what? If you know how to do a formula for a single coil, and then you wanted to do a formula for a bunch of coils, you could use the singular coil loop formula as a starting point to build up a formula for several closely spaced coils. So I'm going to go to the next one now, which is Helmholtz coil. Do you remember what the phrase Helmholtz coil meant? We used this last week. It was the last part of the lab, although you maybe took data at some other point in the hour. It's two circular loops, otherwise identical, kind of like could think of this as like two parts of a solenoid, two turns of a solenoid, spaced out a certain distance. And maybe we'll look at this here. So just one by one, that's the magnetic field for solenoid or loop number 1, which I guess is sitting at position -1/4, I think, of a meter, if you see that there. And then we're going to have another loop there, and it's at +1/4. And then D is going to be, so R I'm not going to change. It's going to be radius of the loop. I am not going to change its current. The vertical direction is magnetic field in kind of arbitrary units. And the horizontal direction is X coordinate. And I'm going to adjust this issue, like how far apart do I want the coils to be kind of right on top of one another or spaced out a bit? And the units here are basically in units of radius. So if you go to like 1, if I make this 1.6, that puts the separation at 1.6 radiuses. And then that's not what I want. This one is to add them up. So this formula is just adding together these two expressions. What's the only difference between the blue expression and the red expression? They're both patterned off of the single coil formula, and I'm doing R² plus distance from the center of the coil, and one of them is at -d/2, and the other one's at +d/2. So the only differences are, the sign in front of the d/2, and everything else is the same. And then I just want to add them together. So here's the combined magnetic field along the axis of these two coils. What is this going to do? Nope. What is this going to do? Nope. I don't remember what some of these visuals are. Okay. Okay. So right now they're spaced out how much? They're spaced out 1.6. So I'm just going to move them closer and further apart and just watch. So they're really close together. Of course, the magnetic field is really strong. They're basically the same as just a single coil right there with double the current. That should be just twice as high. And then you get this, and you get this, and now they're pretty much two separate coils, almost kind of doing their own thing. And does anything kind of stand out in here as somewhat of an interesting point? What if your goal was to try to get a magnetic field to be kind of steady over a fairly decent chunk of the axis? That might maybe kind of right in here, you know, and I think you can kind of see by the decimal number for D over by my cursor, it happens when the separation between the two coils is equal to 1 radius. So one of them's a positive half a radius, one's a negative half radius, and you could say what's the magnetic field right there, but now you have a lot more freedom. What if you put your wand, that little wand that jitters around in your hand, like what if you move it around, you know, half a centimeter? It hopefully would have had less of an effect then to jiggle around half centimeter than if you just are kind of just looking at the red curve and you're trying to move further out or something like that. So this is not a solenoid. This is 2 coils, but this is already kind of showing us like the idea kind of a solenoid, which is if you space them out kind of regularly, you get a big chunk of space inside where the magnetic field is kind of fairly steady. How strong is this magnetic field? The peaks of these guys, for reference, the peaks of these guys are a half. That's probably because there's a 1/2. There's a 1/2 in those formulas. So each one is kind of relatively speaking a half. And our strongest magnetic field, here we have 2 of them, but we spaced them out. We're getting like, you know, what, 0.715 or whatever. And you can do the calculus to figure out what is the ideal spacing to make that really smooth. How would you say mathematically, I don't really want this. I don't really want that. I'm trying to get this. Like, how would you say that? At the origin, or at x equals 0, what are we trying to do kind of, let's say at x equals 0? I don't want that. I don't want that. Yeah, the first derivative is going to be 0 for sure, right? It's either going to be the top of a hill or the bottom of a valley. The first derivative is 0 just to be at the midpoint of any 2 coils. But we're trying to make it really flat, which is not only the first derivative 0, but as many derivatives 0 as we can, in particular the second derivative. And because the whole function's even, you know, like the black function's even, you know what I'm saying? Positive x and negative x are even symmetry. So if you do, what does that mean about the derivatives or this guy? All the odd derivatives are 0 for sure anyways, because it's an even function, and that's kind of what that means. So actually, if you make the second derivative 0, if the first derivative 0, if you make the second derivative 0, you not only have flatness to like the first degree or the second degree, you actually have to the third degree, and the first non-zero term, if you get to the nice balance point, the first non-zero term other than the constant, you know, there's a constant of 0.7155. The first non-zero term would be a slightly negative x to the 4th kind of term. And that's just slightly doing this, but it's doing it more like an x to the 4th, which is really flat through its turnaround, as opposed to a parabola, which is not as flat through its turnaround. So you can do that. And so you take the second derivative of this expression, set it equal to 0, and then maybe adjust D, solve for D. What D value will make the second derivative 0? And you get a pretty simple relationship. You get D needs to equal R. So then you can do that. And then now we're going to look for one that hasn't been saved in the last week, because I forgot to save it last week. We're looking for one that says solenoid. And if you see it, it's probably down here a ways. Oh, it should be around here. Yeah, I think I'm about to get, oh, maybe I'm wrong. I thought it was used last spring, so I thought I'd say it. It's coming up. Anybody see? You want to say solenoid? Whew. I was wrong. Okay, I must have used it last spring, but not really saved it last spring. Okay, so I'm just going to quickly kind of do this a little bit. So what is this trying to show us? Well, that's a single coil. That red is the magnetic field of a single coil, which I don't think I have drawn on there. I'm going to do an even number of coils. So like that's a single coil. This one right here is what we just did on the last worksheet. This is a Helmholtz. This is 2 coils kind of spaced out equal to their radius. And that's our Helmholtz flatness in there. And that would be basically, maybe don't look at this stuff right here. That would be like if you just had one wire right here and another wire right there. One circular loop at the black and the black, just for 2. And this would be what if you did 4 of them. So what if you kind of did 4 of these guys, 4 circular loops equally spaced, equal to their radius? Then you'd get this kind of thing here. This is the magnetic field along the axis of 4 guys. And then what's this one? This is N coils, and we'll just adjust the number for N. So right now, black is, red is 1 coil, blue is 2 coils, black is 4 coils, 6, 8, 10. So imagine the spacing just continues from left to right, like from the left to the right. So this is what you get for the magnetic field along the axis as you just add more and more and more and more coils. And this is simply just adding up the single coil formula and placing a new coil, another radius to the right, another radius, well, one to the right, one to the left. So you kind of see what starts to happen along. If you make it a pretty long solenoid and you're down inside the solenoid, there's slight variations in the magnetic field because basically you're in between 2 and it's a little weaker, and then you get right on one and it's a little stronger, a little weaker, a little stronger. But those ripples become less and less sizable as you add them. And you could also say, like, let's say you just looked at the middle, you only looked at the middle half of this sketch. There isn't much of a difference between 12 coils and 20 coils, right? So, and by the way, relative to this height, which this is kind of at like height 1/2 because it has the 1/2 in the single coil formula. When we went to 2 coils, we could get to 0.715, 4 coils nicely spaced, 0.8. What is our strength here? I'm just gonna kind of look, we're somewhere between height 0.9827 and height 1.0074 over a pretty long range of values. And so basically, this is the 1 that shows up in the solenoid formula. There's no 1/2. There's no 1/2 pi, it's a 1. And to make it really a solenoid, what do? We don't have gaps. We just have smooth wrappings all the way down. But what becomes relevant is what's the density of the wrappings? Did you smoothly put 10 wrappings in every centimeter, or did you smoothly put 50 wrappings in every centimeter? So this is basically, I would say more or less that's a solenoid. And until you get pretty close to the edges, until you get kind of like out here, it doesn't drop below, 90% until like we get pretty close to the edges. And if we're infinitely long, don't worry about it. So what else do we got down here? There's something I was looking for. I thought I had a ratio on here somewhere. Maybe I took off the ratio. I wonder what this is. Oh, that's drawing the box, apparently. What is this? Oh, that's just how big the box is drawn, which doesn't really mean much. It's just kind of visual. Okay. I thought at some point it did the ratio of the high point to the low point. It said, well, we have a variation here, but the variation is like less than 5% or less than 2%. And I think that was on the last one. It's not here. So that is maybe just a little bit of discussion or for this formula right here, more or less, without deriving it. The best way to derive this is to use a new version of, not Biot-Savart, but a new version of this, which is more geometric. It's called Ampere's law. And we'll maybe look a little bit at the more geometric version of some of these equations for electromagnetic field together after break at some point. But this is what you get. I'll also say one more thing about this. Not only does it not matter the size of the circle, it doesn't matter that it's a circular cross section. If you have the same shape cross section all the way along, you get this same result inside, which to me was a very strange fact the first time I heard it. The shape doesn't matter. The shape doesn't matter. You can do some weird shape cross section and just repeat that shape with every winding, and you get this strong of a magnetic field inside. Still true. And outside it cancels out very much to 0, which isn't shown there. But basically, if you were to kind of imagine making this magnet longer and longer, these return loops don't start returning until really far to the right. And if they don't start returning until really far to the right, they're pretty high, and it's a weak magnetic field just above the magnet. And that would be similar to like being a weak magnetic field here. So last thing, which one on here is this most like? Is there any electric arrangement that this solenoid magnetic arrangement is somewhat like? I'd say it's close to this one because this gives you a uniform electric field and this one gives you a uniform magnetic field. And if I were to go a little further, it would probably be even more similar to this one if we did our parallel plate arrangement. Because first of all, this one has a 1/2 in it for a single plate. And if you do 2 plates, you lose the 1/2. That's pretty minor, but true. But also in between the 2 plates, the electric field is uniform, but above the top positive plate or below the bottom negative plate, they cancel out to 0. So you're carrying around this little sandwich of electric field. And here you're carrying around a little tube of magnetic field, kind of. So those would be some of those. All of these involve a right-hand rule. You should probably think of the formulas as only calculating the magnitude, and you are going to do right-hand rule on your own to assign the correct direction to it. And typically, one quantity is kind of linear-ish, and the other one kind of circulates. So if the current is linear, the magnetic field circulates. What if the current's kind of circulating, then the magnetic field on the axis at least is linear? What if the current's circulating around a solenoid, then inside the magnetic field is kind of linear, and you can just kind of do this for, sometimes this is current and this is magnetic field, like the top picture, and sometimes this is current and this is magnetic field for the loop pictures. Yeah. Okay. That's a good spot to leave it today. We have lab tomorrow. It's a fun one. There's almost no numbers. It's a good one. There's going to be a handout before the test of like key equations about circuits, but more so about magnetic field stuff. But this would be another, I think these will be on there. These will be on there actually. Yeah. Yeah.
So what do you want us to do for the lab? Like, I don't know.
Which part of the lab?
I don't know all of it.
Okay.
Besides like the filling out of the data.
So
He's wondering how much
like
analysis.
graphing, like what
I would-
exactly do you want us to like turn into?
Yeah. So let me just go to this one. You know, you could use this to do your. I'd like to see a graph of the magnetic field of the bar magnet data, and it's just going to descend in some way. There's no analysis to do there. Just like make that graph. You know what I mean? Off the north pole of the bar magnet, and then this one is on the coil of the single magnet of the single on the axis of the single coil, and this one we have the formula, and you're asked to calculate the formula. The theoretical magnetic field is one of the columns in the table, but I would say it'd be good to go here and just put your data in and graph this. And you can put your numbers in. What's your radius? What's your number of turns? What's your current? And this is basically graphing or calculating the theoretical for you. And if you wanted, you could click this one, and those should be the values that you've calculated. Is there not a data point right there? Or is it just right on it? Oh, it's just right on it. Okay. You know, like the red is the theory and the purple is your data. I mean, it's probably not going to look quite as good as that, but it should look pretty good. Usually the first couple points maybe don't agree as well, and then it looks pretty good the rest of the way down. That'd be the main. That'd be the main ones, and then you'll have a sheet that you already have with a bunch of arrows on it, or maybe 2 sheets with a bunch of arrows on them.
Yeah.
Those
All right.
guys. Yeah. You can calculate this by hand or on Excel, but these red dots would be the theoretical values in
I
Gauss.
did that on Excel, yeah.
Yeah, you probably did. Did it compare okay, or
No, it was not good.
what? By not good, you mean like?
The first one with The single one was not bad. The one with the middle one, for some reason, was off by like 2.
So the whole set of measurements compared to the whole set of theoretical calculations, one of them was kind of bigger by
Yeah.
a noticeable amount. Do you remember which one?
I think the theoretical one was by